So now we're going to start graphing rational functions. A rational function can be defined by any function where you have two polynomials being divided by each other, and your denominator cannot be 0. So we're going to start by finding the intercepts. So when you're looking for the x-intercepts, you're going to focus on the numerator. We're going to set the numerator equal to 0, and then write it as a point where you have your number and 0. When you're graphing it, it must go through the roots, but it cannot cross the x-axis any other place except for the places where you have established that it is a root. Now, there is a special case when you don't have a single fraction, and we'll have that in example 1. So that's for your x-intercepts. For your y-intercepts, to find your y-intercept, we plug in a 0 for x, and we simplify that and write that as a point. So let's look at our first example here. We have f of x equals x squared minus 2x minus 8 divided by x squared plus 2x minus 15. So again, to find our x-intercepts, we're going to look at our numerator and factor that down. So when we're factoring that down, we can do a shortcut, and it would be two numbers that multiplies to give you -8 and adds to a -2. And those two numbers would be -4 and +2. So to find our x-intercepts, we would set both of these equal to 0. So we would have x minus 4 equals 0, which means we have an x-intercept at 4, 0. And we would set x plus 2 equals 0. X plus 2 equal to 0, which means we have an x-intercept at -2, 0. So these are our roots. And for our y-intercept, to find our y-intercept, we would simply substitute in a 0 for x. So when we do that, we have y equals, and we would have the 0 squared minus 2 times 0 minus 8. And that would be over 0 squared plus 2 times 0 minus 15. And that would just leave us with a -8 over -15. So the y-intercept would be 0 and then +8 over 15. Our second example, this will be a special case because notice that we don't have just a single fraction. We have a fraction and then it's -2. So because this is a special case, it's not a single fraction. Then we're going to set this equal to 0 and solve it. So that would be 0 equals 4 over x plus 3 minus 2, and we're going to solve that for x. So in order to solve it, I'm going to start by adding 2 to both sides. Which gives you 2 equals 4 over x plus 3. And I'm going to write that as a fraction over 1 and cross multiply it and solve it. So that would be 2 times x plus 3 equals to 1 times 4. So 2 times x plus 3 equals 4 times 1. 2x plus 6 equals 4. 2x equals -2. X equals -1. So we have an x-intercept at -1, 0. For our y-intercept, we simply substitute in a 0 for x. So for our y-intercept, we have y equals 4 divided by 0 plus 3 minus 2. So y equals 4/3 minus 2. And I'm going to write this with a common denominator. So y would equal negative 2/3 0. And whenever you're writing an ordered pair for your y-intercept, it would be 0, negative 2/3. So that's how you find your x and y intercepts. So the next thing we're going to do is write our domain. So remember, we have a red light, and the red light is that we have x's in our denominator. So when you're writing your domain, our focus is on our denominator. So we're going to factor our denominator. And when we factor that down, two numbers that multiply to 15 and add to 8 would be 5 and 3. So that means that x cannot equal negative 5, or x also cannot equal negative 3. So our domain would be negative infinity to negative 5 union, negative 5 to negative 3 union, negative 3 to infinity. And that would be our domain. So just like we discussed in chapter 2, for domains, if we have an x in our denominator, we have to exclude those values. And the two numbers we are excluding would be negative 5 and negative 3. So this would be our domain. Vertical asymptotes also come from the denominator, similar to your domain, except when we write that, we actually write it as an equation, not an ordered pair. It will be x equals our x values. And their boundary lines. An asymptote is simply a boundary that the graph will come close to but never cross. So when we're looking at this example 3, we have to focus on our denominator. So this graph only has one vertical asymptote. So if we set this equal to 0, we subtract the 1 and we divide by 2, we get that we have a vertical asymptote. This is where our vertical asymptote will be. So that means that if we were graphing it, if that's negative 1, then we would have a vertical boundary line going down at negative 1/2. For the second one, though, we actually have two vertical asymptotes because we have a quadratic. So when we factor this down, this would factor down to x minus 5 and x plus 3, which means that we would have one vertical asymptote at x equals positive 5 and another one at x equals negative 3. So for this equation, when we went to graph it, we would have two vertical asymptotes. And it would be one at negative 3 and one also at positive 5. So it would be one over here and then one over here. So that, in this example, we would have our graph divided into 3 sections. We would have something happening on the left of negative 3, something happening in between negative 3 and 5, and something happening on the right of positive 5. Okay, so removable discontinuities, that is a hole in the graph, and that only happens when you have a quadratic over a quadratic and they share a factor that can cancel. So in this example, when we factor the numerator, I would need two numbers that multiply to 8 and add to negative 6. So that would be negative 4 and negative 2. And then in my denominator, I need two numbers that multiply to negative 12, and add to positive 4. So that would be a positive 6 and a negative 2. So notice that they both have a factor of negative 2. And because they share a factor, we can remove it. That's why it's called a removable discontinuity, because that factor can be removed. So in order to find it, we're going to take the factor that we can remove. We're going to set that equal to 0. And this is actually going to be an ordered pair. So that means that x equals 2. We have a removable discontinuity. And now let's take that 2 and substitute it into the equation we have left after we factor out that x minus 2. So the y value would be 2 minus 4 over 2 plus 6, which is negative 2 over 8, or negative 1/4. So we have a removable discontinuity, and that would be at positive 2, negative 1/4. So this graph will have a hole in it at that point. Okay, so now it's our in behavior. So there's 3 different types of in behavior. And to figure out what it's going to be, which of the 3, you're going to look at the degrees. So we're going to use the top and bottom degree to decide which category. So if your degree is the same, it's the same degree, top and bottom, then it's balanced. And we simply have to divide our leading coefficients. If it's higher at the top, that means it's top heavy. For example, if we have something like y equals x squared plus 3 over x, then we have to do synthetic division to write our equation because it's a slant. But if it's bottom heavy, higher at the bottom, then it's automatically y equals 0. So let's look at these examples together. We'll look at example 5, 6, and 7. So for example 5, notice that they're balanced. They both have a degree of 2. So because they're both a balanced quadratic, same degree, we're simply going to divide our leading coefficients. So that means that we have a horizontal asymptote at y equals 3/4. And remember, that is just a boundary that you cannot cross. For the second example, it's not a single fraction, but it is balanced because they're both first degrees. So because they're both first degrees, we're still going to divide. We're going to divide 3 by 1, and then we have to include this minus 4. We have to subtract it. So our in behavior will be 3 divided by 1 and then minus 4, which is the same as y equals negative 1. If it's bottom heavy, for this first one, we have a single fraction. So because we have a single fraction, it's simply y equals 0. No calculations needed. For our second example, this is bottom heavy. So this is going to be our 0, but we cannot ignore this minus 4. So it'll be y equals 0 minus 4, or y equals negative 4. Remember, it's a special case whenever it's not a single fraction. And then lastly, we have our top heavy. So we have a higher exponent in the numerator, and this is where we have to do synthetic division. So when we do our synthetic division, we make our L. We take our denominator, we set that equal to 0. And that'll give us x equals -2. That number goes here. And then we list our coefficients. 1, 1, 3. So we always bring down that first number, which is a 1. Multiply 1 times -2, we get -2, and we add. And that's as far as you need to go, because we're not concerned with the third number. This first number is our slope, the slope of our slant, and the second number is our y-intercept. So the equation for our slant asymptote would be y equals 1x minus 1. So we would actually have to graph that on our graphing paper, and we would graph it as a slanted line. Slope of 1, y-intercept of -1. Okay, so we'll end with example 8. Let's look at this first one here. And we're going to graph it. So, do we have a removable discontinuity? No. We only can have a removable discontinuity if we have an x squared over an x squared, and we don't have that in this example, so it's no. Roots come from the numerator. So I'm going to take that x minus 4, set that equal to 0. So we have a root at 4, 0. And that's the only place where this graph is going to cross through. I'm going to put a point at 4, 0. Our asymptote, vertical asymptote, comes from our denominator. And we write that as an equation. So if we take that x plus 2 and set that equal to 0, we get that we have a vertical asymptote at x equals -2. So I'm going to draw in a dashed line at -2. I'm actually going to draw that in red. So I like to think of asymptotes as like the wall of fire. The graph cannot go through. So that is a boundary. Our end behavior, so this is a balanced graph. It's balanced because they're both first degrees. We have a first degree divided by a first degree. So because we have a first degree divided by a first degree, I'm just going to divide my leading coefficients, which happen to be 1. So for my horizontal asymptote, it would be y equals 1 divided by 1, or y equals 1. So I'm going to draw that in -2, dashed also, and I'm going to use my red. So we have 2 asymptotes. And then lastly, we have our y-intercept. So to find our y-intercept, we substitute in a 0 for x. So that would give us -4 divided by 2, or 0, -2. Oops. 0, -2. So -2 would be here. And we kind of have enough happening here, because remember, these are boundaries that we can't cross. So it's going to come through, hit through the x-intercept, and then touch your y-intercept, and it's going to get really close to your vertical asymptote, but it never crosses. So we're going to do a little t-chart to get a few more points, because we don't have anything on the left side of my vertical asymptote. So I'm going to substitute in -3 and -9. And you could choose any numbers on the left side. So I'm going to plug in -3, and I plug it in. I'm plugging it in here. So that would be -3 minus 4 over -3 plus 2, which would be -7 divided by -1, which gives me a +7. So at -3, I'm going to go up to 7, put a point right there. And then I'm just going to pick another number. I think I said -9. So let's put that in. When I put in -9, it will be -9 minus 4 over -9 plus 2, which is -13 over -7, which as a decimal, let's see what that gives us. That's about 1.9, so approximately 1.9. So I'm going to plot that point. So it's going to be right under the 2. And then we're just going to graph that out. So it just comes through, crosses these points. And you can put as many points as you want to. You just want to get the general shape. And that is what your graph will look like.